Hello. Today I'm talking about a stabilized sparse dictionary learning method that we employ in our paper, Kernel Learning for Robust Dynamic Mode Decomposition. In that paper, we present the linear and nonlinear disambiguation optimization framework, or LANDO for short. And the LANDO framework typically consists of 6 key steps. As with all data-driven algorithms, we first need to collect our data, and this can be from a high-dimensional, nonlinear dynamical system or partial differential equation. Given those data measurements, we organize them into matrices. So we have 2 matrices, X and Y. And X can represent the state, and Y can represent the state advanced forward by a time step or the velocity measurements of that state. And with LANDO, we want to determine a function that connects the samples X and Y. And then, given that function, we're going to extract physically interpretable information. Okay, so we organize these matrices by columns, where each column represents a different sample, and then each row represents a different state. LANDO is a kernel-based learning method, and therefore we need to define a kernel function that we believe accurately represents the dynamics. And these kernels can be determined through physical intuition, experiment, cross-validation, or optimization. Here are 3 of the most popular kernels: linear, polynomial, and Gaussian, and any of them can be used in this framework. But a common problem with kernel learning, which we'll go into in more detail later, is that the associated regression problem can be highly ill-conditioned or computationally intractable. And therefore, we deploy a sparse dictionary learning technique where we pick out the most important samples in our matrix X and then use those in the kernel learning. Using this dictionary, we perform a regression to determine the weights of the kernel function and then define and extract our kernel-based model and interpret the linear operator via its spectrum, nonlinear forcing, and can also perform predictions and reconstructions. This can also be framed in a completely online framework for large numbers of samples or streaming data sets. So the main step of LANDO that I'm talking about today is the sparse dictionary learning. In kernel methods, we often have to invert a kernel matrix, which can be ill-conditioned, very high in dimension, and difficult to store in memory. And therefore, these authors proposed the kernel recursive least squares algorithm, which iteratively refines a kernel model by defining a sparse dictionary. So given our samples X, most of these samples will be irrelevant or redundant. That is to say, they can be represented or approximately represented in terms of other samples. So we want to take all these samples and find a sparse subset of these samples, which we call the dictionary. And the dictionary is optimal in the sense that it spans the largest subspace in the feature space defined by our kernel, K. And our method is very similar to the kernel recursive least squares algorithm, but we make a key step where we do not construct an ill-conditioned matrix, but rather it's Cholesky factorization, and I'll detail that later. So this is how we set up the dictionary. We iterate through all the samples, if they're ordered by time, or the order can be randomized. And we represent all the samples up to time t by this matrix capital X of t. And the associated dictionary at time t is represented by the tilde over the X, like this. And tilde m, subscript t, represents the size of the dictionary, or the number of samples in the dictionary at that time. And usually that number of samples will be far lower than the total number of samples up to time t. But this dictionary has an alternative representation in the feature space that is induced by the kernel, and we represent it like so. So phi here represents the implicit feature map from the state space to the feature space defined by the kernel. So as we're iterating through all these samples, we're asking the question, is this sample well represented by the dictionary? And that's represented mathematically by this number, delta t. So delta t represents the distance in feature space of the sample x of t from the dictionary. So tilde capital phi is the dictionary at the previous time. So it's a big matrix. And then phi of xt is the sample at time t in the feature space. So if this distance, if this delta is small, then that means that the current sample in this nonlinear feature space can be well represented by the dictionary. And therefore, the current sample doesn't really represent any new information, and we don't need to include it. But on the other hand, if this distance delta t is large, that is, if it's greater than some threshold, then it does represent some new information, and it cannot be well represented by the current dictionary, and therefore we need to include it in our new dictionary. So we update the dictionary with that new sample at the current time. And this number phi is how these samples in the dictionary are combined to approximate the current sample. So it's just a vector. And the solution to this minimization problem is given by this quantity, delta t. And the relevant quantities, the kct, this bold k with tilde, are all defined in these columns on the right. And this is all completely correct mathematically, but a problem arises in practical implementations when we want to calculate the vector pi. And pi is very important. We use it to determine this distance. So errors in pi t can become very important and can indeed stabilize the algorithm. And in particular, the source of errors is this matrix, this big K matrix, and that's the kernel matrix. It's a symmetric, positive definite matrix. And in many cases where we're using practically useful kernels, such as quadratic kernels, this matrix K is very ill-conditioned. And errors can accumulate in these representations of pi, and we'll see later how that leads to inaccurate representations of the dictionary and a loss of sparsity. So how do we get around this? Well, we use a trick from numerical linear algebra called the Cholesky factorisation. So any symmetric positive definite matrix, here represented by tilde k, admits a Cholesky decomposition. It can be expressed as the product of two matrices, well, the same matrix and its adjoint. And this is a lower triangular matrix. And if we have the Cholesky factorization, then we can calculate that quantity pi without evaluating tilde kt explicitly. And the condition number of the Cholesky factors is usually much smaller than the condition number of the original matrix. Usually it's the square root of that number. And in particular, we can construct these Cholesky factors by updating from the previous time Cholesky factor. So the kernel matrix can be represented between different times in this form. So you take the kernel matrix at the previous time, and then you add a row and add a column, which are the adjoint of each other, and then you add another number here. So we're just supplementing the previous matrix with a new row and a new column. And you can write the Cholesky factor of this new matrix in terms of the Cholesky factor of the old matrix in this form, where this bottom row is this vector s, which is determined like this, and then this number c is determined like this. So we can really quickly and efficiently update our Cholesky factor as we consider new samples, and as new samples are added to the dictionary, the kernel matrix tilde k. And then we can calculate this vector pi much more accurately by, instead of constructing this matrix k, we do two back substitutions with the matrix C, and this ends up being much more stable, having much less rounding error and numerical instability than doing the full inverse matrix K. Okay. So here's an example. We're learning a dictionary for the Burger's equation. So we have measurements of the Burger's equation at a number of different times for kinematic viscosity 0.1, and we're constructing a dictionary with a quadratic kernel that best represents that data. And in the blue, we have the original KRLS framework, the original kernel recursive least squares framework. And then in the orange, we have our Cholesky method, and in the white, we have a batch method. So that doesn't use any updating. That computes the pi's, or it computes the deltas from scratch at every time step. So that batch method is typically too expensive to use in practice, but here it's a useful benchmark. And we see that the Cholesky and batch methods are in complete agreement, whereas the KRLS method introduces a lot of errors, just even when we're at times as low as 7 or 8. And the result is that there is a loss of sparsity, and the method without this Cholesky factor erroneously contributes elements to the dictionary that shouldn't be there. And here we see the loss of sparsity, namely that the Cholesky method is again in agreement with the batch method. So this is the number of samples in the dictionary, whereas the KRLS original method carries on adding a lot of elements to the dictionary that shouldn't be there. So the point is that the Cholesky factorization method is far more stable than the original KRLS method, and it's as good as the expensive batch method. So thank you for listening. I'll leave a link to the arXiv version of our paper in the description. Thank you.